So in this clip, I will show you how to do some numerical computations and to show you how to compute the effective diffusivity tensor of an SVE. So what this method that I will go through now, what it does is that it computes this matrix here. So this relates to Fick's law of diffusion. So in one dimension, you have the diffusivity of the material times the gradient of some potential. This could be chloride diffusivity or moisture, whatever. And then the flux is equal to the diffusivity times the gradient of this concentration with a minus sign in front of it. So the flux flows in the opposite direction of the gradient. In 3D, this is what the expression looks like. So then you will have 9 diffusivity terms, which makes up the diffusivity tensor. And what this method does now is that it computes the average of this diffusivity. So this is an average value of concrete in total, which is a combination now of cement, gravel, and ITZ. So you make this computation by invoking this method, computeEffectiveDiffusivtyTensor. So this is what you need to call. And then you will need to set some material parameters. So if you go into cement class file, which you find in the folder, which I now closed out, but this one sits in the same folder as this file. And here is specified the diffusion coefficient of cement. So now I just have unity here, so 1 as a reference value. And then the diffusivity of aggregates, the ballast is always 0. And then the diffusivity of ITZ can be anything really here. So in this example that I will run now, I set it to 0. So in practice, it means that the SVE only contains cement and aggregates. And again, the diffusivity of the cement is 1. So what this means is that if the SVE only were to contain cement, the effective diffusivity, the average diffusivity of the SVE would be 1. It would be equal to the diffusivity of the cement because it would only contain cement. But as we now have included some aggregates and these aggregates have 0 diffusivity, the average or effective diffusivity will be lower than 1, but still much or higher than 0. Okay, but you set these parameter values in these files here, and then from the main script here, you just invoke this method. So we run it and see what we get for result. So again, it says that it solves the diffusion problem. And now this method has parallel computing implemented. So if you have multiple CPU cores on your computer, it will use all of them, or at least up to 12. This is a limitation by most MATLAB licenses. So I think I have 4 CPU cores on my machine, and it shows, no, sorry, I have 2. So it says 2 workers. So what this in theory means is that it would cut the computation time in half. There is some overhead to this implementation, so it's not the perfect time cut in half, but it will reduce the time significantly. Okay, so I will pause the video now. So now the computations are done, and what has happened now is that there has been a new file created in the folder where all the SVE related data and files are stored. So now this file is new, effective diffusivity tensor, and then underscore nx equal 80, because that's what we had set here, 80. So this is just a normal text file, and it contains a 3x3 matrix. And these values here correspond to the values here in this matrix. So if we take them side by side here, this value equals to this quantity here, and likewise this one equals this. So this is the diffusivity in x, y, and z direction, and these are the cross components. So like I said, if this was purely cement, this value would equal 1. Now we had, if I remember correctly from the previous example, we had something like 7% of aggregates, and we got correspondingly 0.92. So roughly the amount of aggregates, the percentage of that plus this value 0.92 should equal 1, roughly. So now this would be the effective diffusivity of this type of concrete, which has 7% of aggregates in it. And these components are the off-diagonal components, and they are expected to, on average, if you were to do multiple realizations, so if you were to generate new SVEs with different numbers and you were to do this calculation for all of them, if you then averaged all those effective diffusivity tensors, all these off-diagonal components, they would on average be 0. And as you see here, they are very close to 0. And this just means that the material is isotropic. So what this again means is that if you apply a gradient of some moisture or chloride ions in X direction, most of that concentration will diffuse in the X direction. There will be some diffusion in Y and Z direction, but most of it will go in the X direction. And similarly, if you apply a gradient in Y, most flux will go in Y direction and in Z direction. So what we do now is that we redo this calculation, but we change the mesh density. So we had a mesh where NX was 100. So we do the same calculation for NX equal to 100. So now the model will use the data stored in this file and compute a new effective diffusivity tensor. So now the computations are done, and we go into the folder again, and we have now this new file here corresponding to NX equal to 100. And then if we compare these two, we see a slight difference. So here was the one with 80, so which was 0.92. Now it's 0.91 instead. So the difference is rather small here, but you see that there's still some difference, and this value is more accurate than this value. So as a last example, I just want to show you how to use the ITZ implementation for these type of computations. So if you go into the ITZ class, and now this is not the value that I've used actually, but in the previous computation we used 0. While I was pausing the video, I did a different computation using this value, 0.1. But for the computations you've seen, I've used 0. But if we now change this to 0.1 and redo the computations, we will see what kind of effect that has on the results. So if we go back to here, remember that we had 0.92 as effective diffusivity of the SVE. And if we redo the calculations using this value, Fart said 0.1 instead of 0.0, we will see what effect that has. So just change that value in this file and then just redo the exact same computation. So now the computations are done, and if we go back to the folder here and open this one now, so now this is with the ITZ value different from 0. We see now that the diagonal components are in fact greater than 1, meaning that the average diffusivity of this concrete is higher than pure cement, which might or might not be reasonable. But for this value that we put in 0.1, this is the effective diffusivity, which differs from the one without the ITZ. So this coefficient is typically a model parameter that will have to be calibrated with some experimental data somehow. I should also mention something about this value, what it actually means. So in my thesis, in paper C, on page 7. Here's the definition of that parameter. So this value that you plug in here, 0.1, is this quantity here, which is defined as the actual diffusivity of the ITZ times T. And T here is the thickness of the ITZ layer, which is typically very small. So in the paper here, in paper C, I think I assumed a value here of something like 40 micrometers, something very thin. And for that value, if you use 0.1 or 0.15, you get something that is reasonable. So the actual diffusivity of ITZ would be this value that you plug into the model here, divided by the thickness, which you assume some value of. So if you assume 40 micrometers, you will get the actual diffusivity just by dividing this value by the thickness. So that's how this implementation is. So this is why it's different from the diffusivity of cement. So this is the actual diffusion coefficient, whereas this is the diffusion coefficient times its thickness. Okay,